In this talk, I'm going to propose focused MAIHDA as an extension to standard MAIHDA. So to motivate this, imagine you've done a standard MAIHDA analysis, and maybe, for example, you've found that intersectional inequalities account for 5% of the variation in the outcome. I think a very natural question for people to ask at that point would be, well, what about men and women? Who experiences the greater intersectional inequalities with respect to the remaining social identities? Uh, what I'm going to argue in this talk is not only is that of interest, it's unfortunately something which standard MIDA struggles to answer. And I'm going to show you why that is. But I'm going to try and save the day by proposing an extension to standard MIDA, which does much better at recovering, in this case, sex differences in intersectional inequalities. So let's look at standard MIDA. And let's look at the original BMI application by Claire Evans. So 384 strata defined by sex, race, education, income, and age combinations. The headline results were that indeed intersectional inequalities accounted for 5% of the total variation in BMI. Also, of those intersectional inequalities, there were only 65% additively patterned, suggesting lots of departures from additivity. Very interesting. But really, we don't learn anything about whether these statistics differ by sex. Who experiences the greater inequalities, men or women? And are they differentially additively patterned for men and women? Really, the only thing we formally learn about sex differences is that there isn't a sex difference in the overall average outcome. So it is not the case that females have higher means than men, for example, marginally not significant. So a bit uninspiring for a study of sex differences, you could argue. But we might kind of be a little bit more careful and actually get out the predicted strata means, or in this case, the departures from additivity. And this is a kind of from the article, but I've color coded blue and red for men and for women. And these dots are strata means and different subsets of the data. There's 16 because it's 4 age groups by 4 education, 4 by 4 is 16. Don't worry too much, but essentially, it's quite tempting to try and stare at this and see patterns with respect to sex differences. So here I can see that, in different subsets of the data, there do appear to be some quite pronounced sex differences and in different directions. Okay, so the overarching answer of no sex women don't have higher BMI than men, true on average across everyone, but in different pockets of the data, we are seeing pronounced differences in different directions. And more interesting, so we could be seeing differential variability. So across the subsets of 16 strata means here, they are more variable in general for women. So the red arrows are longer and the blue arrows are shorter for men. So that's hinting at differential variability as well. So it's very tempting to even kind of try and put some numbers on this and almost do like a post hoc analysis. We've got 384 dots. Let's just start analyzing it with summary statistics. Now here we've got to be very careful because as we've shown in previous work, the variability you observe in those predicted strata means is a biased estimate of the variability in the true means. So in order to formally study sex differences, we can't just stare at the dots. We need to build sex differences into the underlying model. So most obvious way of doing that would be to do a stratified analysis, simply fit one model for the first 192 strata for men and a second MIDA model for the next half of strata for women. And then you've got 2 of every parameter and you can compare the values. Likewise, in MIDA model 2, where we put in the additive effects of the remaining variables, ethnicity, education, income, and age, and we've got sex-specific coefficients, and again, we can compare and contrast. But there are problems with this approach. First, by fitting 2 entirely separate analyses, it doesn't really facilitate testing for significant differences across the equations, which is course, essential. Secondly, by doing two entirely separate analyses, we are implicitly assuming that the patterning of inequalities for men is independent of the patterning for women. And surely they're going to be positively correlated. In general, strata which show higher BMI for men also show higher BMI for women. Uh, and if we're ignoring that correlation and we're predicting strata means, which we typically do, these are going to be suboptimal because we're misspecifying dependencies in the data. So the solution is to simply sellotape the male and female model together, introduce the extra correlation parameter, and we're away. And that's going to be the focused approach. It's a little bit tricky because essentially we've got to redefine the strata as superstrata. We've got to remove sex from the strata. So we had 384 strata. We now only have 192 superstrata. But within each superstratum, we have two subgroups, the male subgroup and the female subgroup, which corresponds to a male stratum and a female stratum. So we need to do that. And we need to do that if we wish to introduce this correlation parameter. So we do that. So essentially, we now link the two equations by specifying it as a bivariate normal distribution. We have a covariance of the male and female random effects, which allows them to be correlated, and therefore the actual means are allowed to correlate. So let's look at the results. Here is the male and female grand means, and this is an uninspiring start because they're effectively the same, and indeed no significant difference, something we can do because of a joint modeling approach. So surely we wouldn't have doubted that they were not significant in this case. We do see differential stratum variances, and considerably so. So the male between stratum variance is only 0.72, the female 2.78. We could translate to standard deviations, and if you do so, you see that the female inequalities are twice as large as male inequalities. That is substantial and clearly significant. Translated into VPCs, so to what extent do inequalities for men account for male variability in BMI only 2.8%? To what extent do the larger female inequalities account for the larger female variability in BMI? Well, 6.3%. Okay, so inequalities again are larger in this kind of relative metric. Here's the correlation parameter. This is interestingly only 0.53. So there is an alignment between male and female inequalities, but it's not, it's not 0.9. It's not the case that what we see for females is simply what we see for men amped up. It is a different ordering as well as being more variable. Here is the improved partial pooling. So here, how do we get the predicted stratum mean for a man for a given stratum? Well, is equal to their sample mean shrunk towards the male grand mean, but simultaneously, and here's the nuance, shrunk towards the female sample mean within that superstratum, and shrunk also towards the female grand mean. Okay, and done optimally so. And this kind of double shrinkage comes from the presence of this covariance parameter here, recognizing that these are not independent quantities. So in terms of a picture, here's a scatter plot on the far left of the male versus female sample means, shrunk towards a single point, grand mean, giving a resulting cloud of predicted strata means, where the female variability is clearly much larger than the male variability. Here is how do our results actually change from standard to focus. I try to do it this way for men, so they get dampened down. There's a very slight reordering, but trivial. And for women, there's a lot of stability in our league table, but it's slightly more amped up. By allowing for differential variances, that filters through to the actual league table of stratum-specific results. Then we shift into focus MAIHDA model 2. We add in the additive main effects of the four remaining social identities, ethnicity, education, income, and age, sex-specific coefficients. And then we can compare the sex-specific coefficients. And these plots are very different. Okay, standard MIDA assumes they look the same, they differ, particularly for race, where for uh, amongst the female strata, the female black strata are very elevated BMI versus white. And also for income, where for men is a slight positive income gradient across strata, whereas for the female strata, there's a stronger negative, so opposite direction income gradient. So very interesting differences. Um, we have differential explanatory power or differential additivity. So whilst male intersectional inequalities are smaller in general, they're also actually less additively patterned, relatively so, than female. So that surprised me. I kind of assumed that amongst women, we'd see more departures from additivity, more uniqueness of experience, less predictable by general trends. That wasn't the case. It was the opposite. But and this is really crucial, we really need the testing for significance here because it's not a significant difference. Here is the improved bivariate shrinkage. I say improved because we're now shrinking the sample means towards the additivity cloud, which we know explains 80-90% of what's going on. So in terms of our graphics, scatter plot of male sample means versus female sample means shrunk towards the additive cloud gives the resulting, on the far right, predicted strata mean cloud. Looks very similar because we've got 80-90% explanatory power of this for explaining the true sample mean, the true mean variability. Um, Here, final plot, I think, yes. Here we again see how things change as we shift from standard MIDA Model 1 to focused MIDA Model 1, Model 2, sorry, from standard to focused MIDA Model 2. Again, we see the dampening down and the amping up, but there's now more reordering, especially for men. And I say especially for men, where's that come from? It's come from the fixed part of the model and the male coefficients looking different for the female due to additivity, and probably because women are it's not a 50-50 split. Women are a little bit more dominant. Maybe we've got 55% women, and so by allowing sex specific, we're going to see more movement always for the minority group, which is what we're seeing there. So to summarize. I would say once you've done a standard MIDA and established intersectional inequality in general, it becomes quite natural to ask, does that differ across, let's say, males and females? Um, and I hopefully shown you why standard MIDA struggles to answer, but that it's easy enough to shift into the sex-focused MIDA for that second order question, and then you get sex-specific parameters all over the place, which can be contrasted. Um, of course, if race is your focus, then you can have three equations, okay? Or you might even be fully exploratory and cycle over each of those five social identities in turn to kind of find where the differences are. Uh, I wanted to put up a working paper, so you can find one on the on SOC Archive on this. And I'm also about to put up R and Stata scripts with simulated BMI data to replicate this paper, but also both from a frequentist and a Bayesian perspective. So if you prefer to work with maximum likelihood, you can for these models as well. And that's it. So thank you very much for listening.